All right, this lesson is on dividing radicals, and when we divide radicals, we're going to have to be aware of what we can and can't do as far as the denominator of a fraction. All right, let's get started. As we look, there's a golden rule for radicals. You can't have them in the denominator. It's like a big no-no. So you have three ways to fix it. Number one, the denominator is a perfect root. Like, for example, if it said square root of 9 in the denominator, that's going to resolve to be just a 3 in the denominator, so there would not be a square root. The denominator completely divides into the numerator. So if I had like the square root of 200 in the top and the square root of 2 on the bottom, in this case I could actually divide a square root by another square root, and that would give me square root of 100, which works out to be 10, and I would not end up with a square root in the denominator. But what happens when you run across problems where you cannot get rid of it? What if I had like 3 over the square root of 2? In this case, it won't divide, and there's no way that I'm going to be able to make it be a perfect square root without doing something to it. And that's where we're going to have the lesson today on rationalize the denominator. All right, I hadn't previously erased my work when I did this, so I had to begin here. All right, number one, I have a third root problem, and it's third root of 4 over the third root of 8. In this particular problem, what we have to do is see if we have perfect radicals. Now, we haven't done as much work with cubes, so when you deal with cubes, I want to talk to you about what we do. It's very, very similar to what you do when you have squares. If you have cubes or cube roots, what you want to do is you want to make them have perfect. So first thing you want to do is look for, like we used to look for squares with square roots, we're going to look for perfect cubes. So the first thing we're going to do is we're going to look for perfect cubes. They have a list of them on the board. 1 times itself 3 times is 1. 2 times itself 3 times is 8. And so forth. 3 times itself 3 times turns out to be 27. 4 times itself 3 times turns out to be 64. 5 times itself 5 to the third is 125. So we have a list of cubes on the board. So we want to think about those perfect cubes. Number 2, if we're doing cube roots, it takes 3 factors alike inside to pull one out. To pull one out. So we kind of talked about that in terms of square roots. It took 2 alike to pull one out. Since our index right here is a 3, we have to make sure that we adjust how we look at it. So I don't think there is a number in the numerator. There isn't a number. This is not a perfect cube on top, but it turns out 8 is a perfect cube on the bottom. So what is the cube root of 8? Well, that would just be a 2. That is not a perfect cube root in the numerator, but that's okay. We can actually have a cube root or a radical in the top. We just can't have it in the bottom. Number 2, looks like we have a square root, so we're kind of sort of back to looking for perfect squares, or to see if we can have 2 factors alike, pull one out. I need to remember that the square root, the sign, goes all the way across the top and the bottom. So technically it goes with the square root of 20 on top, and it also goes with 9 on the bottom. Square root of 9 is a perfect square, so that's just going to resolve to a 3. I do expect you to factor out, look for squares, 20 would be 4 times 5. Square root of 4 comes out as a 2, and a 5 would be left inside. 2/3, or 2 over 3, with the square root of 5 in the numerator. All right, cube root of 16 and the cube root of 125. Do I have a perfect cube? Well, it turns out 5 to the third power, sure enough, is 125. So the cube root of what number is 125? Turns out to be just a 5 in the bottom. So by remembering our perfect cubes, we can actually resolve this denominator to be something that works out nice and neat. All right, third root of 16. 16 is not a perfect cube. So since it's not a perfect cube, I'm going to get the third root of 16. Make sure you don't get lazy. Make sure you take time to put the 3 in the corner. If you don't, it's really not the same thing at all. All right, number 4. Square root of 6 in the denominator is not a perfect square. Square root of 8 is not a perfect square. But what about the strategy where we could maybe divide the two? Can I divide the square root on top by the square root on the bottom? Yes. You can divide inside times inside or inside by inside, just like you can times inside times inside. So if I divide this part, I'm going to end up with square root with a 3. 12 over 10, this part can be divided. Even though it doesn't divide evenly, it can be reduced. 12 tenths reduces to 6 over 5. No square roots left in the denominator. It is resolved. All right. Number 5, can I divide? I believe this is a very straightforward case of outside numbers can be divided by outside numbers, and inside numbers can be divided by inside numbers. So I get the square root of 4. I hope that you remember that that is a perfect square. Because it's a perfect square, it's the same thing as 10 times 2, which gives me 20. That one had no square root at all, remaining in the final answer. Number 6 is the problem where we cannot do any of the previous things. There is no square root to divide. It is not a perfect square root. So we're going to have to do the third thing, the third strategy it was referenced to in the beginning. We're going to have to rationalize the denominator. In your notes, it says that when you rationalize the denominator, you are going to have to figure out how to make the square root or the cube root or whatever radical you have become a perfect square or become a perfect cube, whatever you need to be. So I need to actually concentrate. The 2 is okay in the denominator. Square root of 3 is my problem. So what can I do? What could I possibly multiply square root of 3 by so that I can get a perfect square? I think you can multiply by square root of 3. If you multiply by square root of 3 on the bottom, the only way you can do that is to multiply by square root of 3 on the top. Everybody see? What I'm essentially doing right here is the same number divided by the same number is essentially equal to 1. So I'm really multiplying my original problem times 1, only it's in a different form. So all we're going to basically do is just change forms with this problem. I'm going to multiply across the top, and when I do, I get 5 square root of 3. I'm going to multiply the numbers on the bottom. My 2 is still down there. My square root of 3 times square root of 3 gives me square root of 9. I made that be a perfect square. Now, I can go ahead and say, you know what, that's going to be the same thing as 2 times 3 down there. 5 square root of 3 stays on top. Final answer, 5 with the square root of 3 on top, 6 on the bottom. Nothing but a 6, and that's okay. Essentially, when you go back and you compare to what we began with, it's almost like I just moved the square root of 3, did a little magic to it, moved it upstairs, and that's what you have to do. You can move your square root, but you cannot leave it in the denominator. So no. Number 7. What would I multiply by to make square root of 2 be a perfect square? And the answer is another square root of 2. So if I multiply by square root of 2 on the bottom, I'm going to multiply by square root of 2 on top. Multiply the top, multiply the bottom. 6 with the square root of 10. 2 times the square root of 2. 4, excuse me, square root of 4. When I multiply 2 times square root of 2 times square root of 2, that's a perfect 4, which comes out as a 2. So I get 6 square root of 10 over 2 times 2, because that's what it gave me. 6 square root of 10 over 4. Technically, I can't really do a whole lot with that, but you can actually divide outside numbers by outside numbers, and while they won't divide evenly, they can actually be reduced. So 2 goes into that 3 times, 2 goes into this twice, and I still have square root of 10 on top. Final answer is 3 square root of 10 divided by 2. Number 8 is an interesting problem, and there are a couple of ways, a couple of ideas that you could do to solve it. But the thing that I want you to ask yourself is, what could I possibly multiply by square root of 8 to get the closest or the easiest square root? Well, someone said, what if the square root was 16? That is a perfect square. What would I multiply square root of 8 by to make it a square root of 16, which is the smallest square root that I can make with 8? So square root of 8 times what? Sure, square root of 2. But if I multiply the denominator by square root of 2, I'd have to multiply the numerator by square root of 2. All right. In the denominator, I'm going to have my 7 out front, and the square root of 8 times the square root of 2 gives me square root of 16. That is a perfect square because we made it become a perfect square. 5 on the outside, and in the numerator, square root of 3 times square root of 2 is square root of 6. Not a perfect square, but that's okay on top. So I'm going to get 5 square root of 6 over 7 times 4 And my final answer would be 5 squared of 6 over 28. 28 is okay on the bottom, doesn't cancel or simplify any farther, and I'm good. Number 9, what can I multiply square root of 3 by so I get rid of my radical? Quick and easy answer would be another square root of 3. So if I multiply it by the bottom, you have to multiply on top. And I'm getting 6 radical 15 over 2 square root of 9. I believe I end up getting, can you kind of figure out now that's going to end up being a 3, and I can shortcut this to be 6. If you have a 6 top and bottom, those are reduced to be a 1. Final answer is just square root of 15, nothing in the denominator. Number 10 is something that we have to pause, take a moment in. Let's go back and review. Now we're doing a cube root. So when we do cube root, what you need to remember is, first of all, try to make it be a perfect cube. Make or look for perfect cubes. All right, remember our perfect cubes are like 1, 8, 27, 64, 125, 216. Second thing, it takes 3 factors alike to pull one out. So 3 have to be alike on the inside to bring 1 on the outside. So when we do cube roots, it's very, very similar to doing square roots, but not the same. Okay. I am going to think of it like this. I'm going to think of that as the third root of 2. And on the bottom is the third root of 3 with a t. All right. We're trying to make it, or we're going to look for perfect cubes. So what could I multiply by? And I have to multiply a cube root by a cube root. So make sure you're thinking cubes. What could I multiply 3 by to make it become a cube? Well, if I think about my cubes, 1, 8, 27, 64, 125, Turns out 27 is the closest cube that I can multiply 3 by and get a 27. What if I multiplied by 9? 3 times 9 would actually give me 27, which is a perfect cube. The next thing to consider is the t. Because it says that it takes 3 factors alike to pull one out, and I only see t to the first, how many more t's do I need to make a perfect cube of t's? How about 2 more? Because when you multiply, you add exponents. All right. That would be what I need to make a perfect cube in the denominator. So if I multiply by a perfect cube on the bottom, I'm also multiply by that same perfect cube in the numerator. In the numerator, cube root times cube root, you can multiply and keep it underneath the cube root. So I get 18t squared. In the denominator, I have a cube root of 3 times the cube root of 9, which is going to be 27. T to the first and t to the second, add exponents gives me t to the third. This should be a perfect cube. I should have looked ahead and seen that it was going to be a perfect cube. So, what is the cube root of 27 going to come out as? 3. Takes 3 on the inside to bring out how many? 1t. So what comes out on the bottom is just a 3 and a t. I cannot get rid of anything in the cube root on top, but that's okay. I can have a radical on top. That is what I have to do to make a perfect cube, to get rid of the radical. All right, number 11. First thing I want to do is I want to say, okay, I'm going to split that, and some things will cancel. Square root of 4 over the square root of a b to the second. Now, if you take a real quick look, there are a couple of ways to do it, but I believe I can actually bring out square root of 4. Square root of 4 is going to come out as a 2, so the top is just a 2. A, there's only 1. I can't bring an a out, but I have 2 b's, so for every 2 b's, I can bring out what? 1 b. So I still have just a square root of a. What do I need to multiply square root of a to make a perfect square? I need to multiply that by square root of a. So if I multiply the bottom of square root of a, I multiply the top of square root of a, I get 2 square root of a on the numerator, and b times the square root of a to the second power, because you're going to add exponents when you multiply. Now I have a perfect square. For two a's, I can bring out an a. And the answer is 2 with the square root of a on top, an a and a b on the bottom. If you put b and then a on the bottom, same thing. Going. All right. Number 12. We're going to multiply by something to make this become a perfect square root. There is not a number in the index, so 2 multiplied by what number would make a perfect square? 2. K to the first needs how many more k's to make it a perfect square? K to the first. N to the third needs how many more n's to make it a perfect square? One more. So it looks like I need square root of 2kn. So if I need that on the bottom, I'm going to multiply by that on the same thing on the numerator. On the top, I'm going to get 6 on the outside, the 2, the k, the n on the inside. And now I'm going to have square root for k to the second when I add exponents, n to the fourth when I add exponents. Whatever you got to do. And 2 comes out, 1k comes out, but how many n's can come out? N squared. Last step, I think if you'll notice closely, outside numbers can be divided by outside numbers, so that turns out just to be 3 square root of 2kn over kn squared. Final answer. All right, very good. We did not do 13. We went straight to rationalizing using conjugates. Conjugates are actually another way of talking about a matched pair. When we did multiplying earlier, we did things like this: x minus 3 times x plus 3, where they were almost the same. They were a matched pair. Something special happened when we started foiling these out. So if you'll remember, x and x is x squared, 3x. Then I would get negative 3x. I get minus 9. Turned out the middle term canceled to 0. So all I had is a square in the front. I had a square in the back. And I ended up with a minus sign in the middle. This was called a difference between two squares. I do not have middle term. So let's see what happens when I apply that same idea of a special multiplying case to radicals. So let's multiply number 1. 5 times 5 is 25. 5 times radical 3 is going to be positive 5 with a radical 3. If you have an outside number and an inside number, you just have to keep both parts. So 5 stays on the outside and 3 stays on the inside. You put them together. All right, negative square root of 3 times 5 is negative 5 square root of 3. The big number or the outside number comes first. Negative square root of 3 times positive square root of 3 is negative square root of 9. Now, I believe that you can see what here happens just like we just previewed. We have a matched pair, but they're not identical. Like they're identical except for the sign. So that sets up a perfect situation for the square root to be gone. I have a perfect square in the back, so that's just going to give me minus 3. I have a number in the front that's going to give me 25. When I subtract, I have two radicals that were multiplied, and the answer is just a number. I do not get a square root. So that's very helpful to recognize that those special matched pairs called conjugates can give me just numbers. So we're going to do this one. 16, 5, and 5 on the inside give me 25. 4 radical 5 and negative 2, 7 is negative 8 square root of 35. All right. Now I'm going to do positive 2 square root of 7. So it's going to be plus 8 square root of 35. And then 2 times negative 2 is negative 4 on the outside. Square root of 49 on the inside. All right. I hope you recognize this is a perfect square, and this is a perfect square. All right. We're going to let those cancel. We have our two perfect squares, so this becomes 16 times 5. Back here it becomes subtract 4 times 7. And then I get 80 minus 28, which I think subtracts to give me 52. All right, so just make an observation here. If you have a matched pair, these are called conjugates. These are expressions such as you have the plus and the minus of the same things, or they're like a matched pair. You do not get a radical. So we can use this to our advantage. All right, I want you to notice in example 1 here that we actually have a sum. I have 2 plus square root of 3. So it's not easy. I can't actually just come in here and say multiply by square root of 3, because really that bottom part is like it's separate from the top. It's almost like that bar acts as a grouping symbol. So it groups the top separate from the bottom. So if you multiply the bottom by something, you have to multiply everything on the bottom by something. So it's not just as easy just to come in here and say, oh, let's just use square root of 3. So what we're going to have to do is we're going to have to multiply by the conjugate. So let's talk about what the conjugate is. What would the conjugate be for 2 plus radical 3? Well, it's a matched pair, but it's not exact, so I still have a 2 and a square root of 3. But instead of being plus, I need a minus square root of 3. So if I multiply the bottom by the conjugate, 2 minus square root of 3, I'm going to multiply the top by the same thing, square root of 3. It's the only way you can multiply the denominator by something is to multiply the numerator by something. Again, anything divided by itself is 1, so it's like multiplying by 1. All right, I'm going to have to distribute here because it is multiplied by everything that I put in parentheses. So I'm going to get 2 square root of 5 minus the square root of 15, inside times inside is 15. And on the bottom, I have to FOIL it out. I hope that it's become a little bit clear that when we FOIL things out with conjugates, we really only need to do the first times the first and the last times the last, because these middle terms are doing what? Canceling out. Okay, so I really only have to do the first and the last. So I'm going to do the first and the first, which is 2 times 2, which is 4. I'm going to do the last and the last, which root 3 times negative root 3 is negative square root 9. All right, on the bottom, I get 2. The top just stays the same. You cannot add or subtract a square root of 5 minus the square root of 15, because when you add and subtract, they have to be alike. So it would have to be a square root of 5 added to another square root of 5. So otherwise, you just have to leave them separate. 4 minus 3 is going to end up being 1. So really, there's nothing on the bottom. The answer is just 2 square root of 5 minus square root of 15. Divided by 1 is still the same thing. All right, example 2. Let's imagine the conjugate. Please remember that the groupings, that the divide bar actually groups the top part and the bottom part. So it's like there's parentheses around it. If you will remember that, it'll make your life a lot easier. What is the conjugate of 5 minus square root of 3? Well, it's matched, but it's not exact. So it would be 5 plus square root of 3. So I'm going to multiply the top as 5 plus square root of 3. All right. So when we multiply the top, this time we have to FOIL the whole thing out. I'm going to get on top 2 times 5 is 10 with the square root of 3 also. Then I get plus 2 square root with 9. Then I'm going to get plus 5 plus 1 square root of 3. On the bottom, I think we've seen by doing enough of these that we end up with the first times the first, because those are conjugates, they're special. They're going to have the middle term cancel. Square root of 3 times negative square root of 3 is minus square root 9. All right, I will have a denominator this time. On the denominator, I believe that becomes a 3, and 25 minus 3 just gives me 22 in the denominator. All right, we want to make sure we add like terms. So 10 root 11, or 10 root 3 and 1 root 3 is 11 square roots of 3. Then I have, this becomes a 3, and 2 times 3 is 6. 6 plus 5 is 11. That would be, I can actually simplify that just a little bit. This is actually the common denominator, which means it goes here and here. So 11 over square root of 3 has a denominator of 22 plus. This 11 over here also has the same denominator of 22. This can actually simplify, and this can actually simplify. So I can get square root of 3 over 2 plus 1/2, or square root of 3 plus 1 over 2. Either way you write it, it's the same thing. You are going to have to be pushed to go simplifying. All right, see if we can get through example 3. All right, if you want to pause and work example 3 and 4, these are the answers. You do need to finish the homework. One side you're doing all of the problems, and on the side where you have conjugates like these examples, you're going to have to do the bottom half.